Yes.
A very good evening to one and all. So it's a pleasure to invite Dr. Adnan Mahmik from University College of London to talk about memristors from memory to the future of energy efficient and brain inspired computing. Adnan Mahmik is a lecturer in nanoelectronics and a Royal Academy of Engineering Research Fellow in the Department of Electrical and Electronics Engineering, UCL. He works on the development of energy efficient computing systems, neuromorphic systems based on memristors. He holds 5 international patents and is a co-founder of Intrinsic Semiconductor Technologies, the startup set up to commercialize silicon oxide memristor technology. Without further ado, I welcome Dr. Adnan Mahmik to deliver his lecture.
Hi, hello everyone. Can you see my screen now? Is it all fine?
Yes, yes.
Excellent. Okay, so first of all, I thank you for this very kind invitation and give me opportunity to talk a little bit about the research that I and my group here at UCL are working on. So I'm going to talk about memristors, which is a novel non-CMOS technology that could be applied for memory applications, but as I'm hoping I'm going to make a case, it could be applied for applications beyond just digital memories. So the presentation is going to be divided basically in two parts. So the first part of the presentation is going to be about the bigger picture. So just to try to fit the memristors in the context of computing and computing power demands. So I would like to start with artificial intelligence.
Sorry to interrupt you, Dr. Adnan.
Sure.
We're not able to see your screen.
Okay, let me then see what's happening. Okay, just a second. Right. How about now?
Yeah, it's perfect now. Thank you.
Okay, so if I just start from the beginning, is it still fine?
Yeah, we are able to see your screen.
Okay, sorry for that. Okay, so as I said, I'm going to try to make the case for memristors, but the presentation is going to be divided in two parts. So the first part is basically trying to paint a bit of the bigger picture. So I would like to start with artificial intelligence, what is probably the most demanding part in the computing we have today. And the reason why artificial intelligence is so interesting is because we can apply these techniques for a very wide range of applications. So anything from autonomous machines to security defense, even the things that we do every day, such as internet and cloud services. So it's really hard to even imagine that we go through the whole day without using some of these services, being aware of not. But even beyond that, artificial intelligence is applied to solve a big complex problems. So this is one example from a few months back where Google's DeepMind system was able to solve a big problem in biology that was the open question for more than 50 years, how the certain proteins are folding. And indeed, we can now see that AI is being applied in science. It's really helping the scientists to work on the certain models and theories. So there is every initiative for us to keep developing AI in the future as well. So I'm sure that most of you are aware of this. So this is one of the most used algorithms in whole AI or machine learning. That's artificial neural network. So it is, roughly speaking, inspired by biology and the human brain. We have basically two functional units. Those are the nodes and weights. And then adjusting the values of these weights that are connecting these nodes, we are able to define the certain functionalities with acceptable performance. Typically, ANNs do operate in two phases. So the first phase is a training phase in which we are adjusting the values of the weights by exposing the algorithms to the set of data at the input, and then by tracking what is happening at the output, we are basically able to minimize the errors that we are getting. That's the training phase. Once we are happy with this performance and the functionality and what our neural network is doing, we are able to employ these algorithms on the various systems and to do different applications. So the one sort of quite obvious example is a pattern recognition and classification of the certain images. So if this neural network is well trained, it is able to then classify even the data sets and the images haven't been seen before. I'm not going to go too deeply into mathematics, but we have a quite elegant mathematical framework how to minimize the errors and how to adjust the weights. It's called backpropagation. What is mathematically relevant, or what is the part of the algorithm which is the most relevant for our computer hardware, is the operations of vector matrix multiplication. And that's basically quite closely related to what we call multiply and accumulate operations. So basically, when we are operating these ANNs, and if we go down to the fundamental level of the mathematics that is happening, the certain algorithm would need to do these operations many times during the, let's say, the inference, for example. So it basically needs to multiply some vectors and matrices, and this is the format that is quite suitable for our current digital systems. So these are some of the takeaway messages. Basically, any machine learning algorithm, most of them, the main mathematical operation that happens is this multiply and accumulate operation, max operations. They happen many times. So you can now even see some quite famous and popular deep neural network models, and how many max operations we would need to do even in a single inference of an image. So then it makes sense to try to think about the hardware and how do we optimize these operations on our computers and computer systems. So what has happened now, again, stepping back and thinking about the bigger picture, what has happened over the last few years, we have seen how the size of these neural networks have increased dramatically. We became very successful, but we also became very ambitious. So you can see that pretty much since maybe early 2010s and maybe 2012, the size of these neural networks increased dramatically. So we went from using maybe tens of millions of weights to these days using something in hundreds of billions. And as the size of the neural network scales up, what is related to that very directly is that the energy usage that we need to have for these systems also goes dramatically up. So this is the same message told in slightly different way. If we think about what are the compute demands that we have today, we can see these trends. So again, the trend pretty much till 2012 was that the compute power demands would double every 24 months. And that was in line with Moore's law, with the law of scaling of transistors, that we would have this sort of, the demand would basically follow what we had from Moore's law. But then since 2012, we can see that the rate of the increase of the power computing demands happens much more dramatically. So the doubling happens every 3.4 months, or even 2 months if you are just considering last few years. So then this is indeed very challenging for our computers and computer systems. So maybe to give you a bit more intuition, what it all means without showing just the graphs. This is the famous example that we had from the few years back. Very successful Google's DeepMind system AlphaGo that was able to beat a human champion in a very creative, very intelligent game of Go. And that was truly impressive, still is impressive. But the part of the story we don't maybe think about too much is what are the resources that have been used to compete against the human. And you can see that inference, and especially training, there is many orders of magnitude discrepancy between the two systems. But even without doing something very complex, such as AlphaGo, and just doing a bit more simplistic applications such as the classification. So for example, quite a famous data set ImageNet and the model ResNet, we can see that for training of the such neural network, which is not that complex and that large, we would need to use many GPUs, or maybe even a clusters of GPUs, that would take a long time to train such a neural network, and it would consume a lot of energy. So again, to put this in context, to train such a network, the energy that would be used, it's close to 2 weeks of home energy consumption. So this is quite interesting fact that maybe we don't think too much about. So how do we deal with this? I mean, not all of us have well, the basement full of the computer clusters or GPUs. So we use the paradigm which is called cloud computing. So basically, the computing doesn't take place on our local devices, but what we do is we collect data locally, and then we send this data over the internet to the remote data centers. The computing takes place there and in the data centers, and we are getting the results back over the internet. So this approach works. I mean, it's applied for many different devices, from laptops, mobile phones, and so on. But then again, there is a bit of the risk and a bit of the concern that even this approach wouldn't be sustainable. We are making our data centers to be one of the largest energy consumers in the world. And also, as a direct negative in consequence, we have that we are producing a lot of carbon footprint by just training a large neural networks. There's also, on the other hand, the concept of edge computing, where we might, for a certain set of application, might not want to use a cloud computing. So there is at least 3 reasons why this is the appealing approach, this edge computing. So maybe we are concerned about the sensitivity of the data that we process. So we wouldn't be too happy to maybe send our data over the internet to some remote data centers. We might be concerned about that. There's a lot of applications where the decisions need to be made very quickly. So you can imagine that there is a drone that is flying by a very fast speed, and that it needs to make a decision: does it just turn left or right? And if there is a latency in the system which could be related to this cloud computing approach, it might not be good enough. So it is quite restrictive in that sense. And finally, there is the question of infrastructure. So maybe we don't have the access to the internet all the time, but we would still like to use some of these services of AI. So this is basically the summary of this problem. We have our current computer architecture, or the hardware, that uses hundreds of watts of energy, even when we think only about our, let's say, GPUs that we use today, and other applications where we would like to have AI are run on the systems which are run with the power budgets of less than 1 watt. So there is this discrepancy. We basically would need to think how to become much more energy efficient if we are going to put the computing directly on our portable devices. So again, the artificial intelligence, I mean, how can we improve? And then we need to think about what are the 3 main driving forces that allowed this dramatic improvements of AI and development of AI. So of course, the first one is algorithms, but many of these algorithms that we use today, we had back in 1980s. Of course, we keep improving on them, but this is something that is not really the bottleneck. It's not the limitation that we are seeing today. Also, data that we use to train the neural networks is available, especially with the internet. So that's not a big problem. And lastly, it seems what really is the limitation is the current hardware. So if we can't supply enough compute power, then it's not practical maybe to run or to train these particular systems. So then maybe we need to think about what's the way to improve on the hardware systems. And this is basically the 3 approaches that we have. The first one is, of course, Moore's law. The Moore's law is still alive. We are still seeing that our transistors are becoming smaller. But the thing is, this trend is slowing down. And it's a big question if you are going to be able to continue with shrinking of transistors for many more years. Once we get to, let's say, the node size of 2 or 3 nanometers, it's a big question if this is going to be economically viable solution. I already told something about the data centers. So this is this picture on the right. and the approach just of scaling up the data centers might not be that smart and that feasible. So today, the most of the gains are actually achieved through the circuit design, more specifically chip architecture. And we can now think what is that that's happening over the last few years. So again, this is the trends and the conclusion of what has been happening. So we can see the Morse law, basically, which is related to the number of transistors of microprocessors. How this trend hasn't stopped, but it's basically slowing down a bit. We had something which is closely related to Morse law, which is called Dennard's law, which meant for many years, it was true in the past, as we made our transistors smaller, they also became much more energy efficient. But this trend pretty much stopped 15 years ago. So what we are seeing that the frequency of our microprocessors is not going up. And the game that is played these days, it's related to the computer architecture or the chip architecture. And it is reflected, for example, in number of cores that we have on the single chip. But we can think of, okay, about the more holistic way to improve the performance. So of course, we need to think about the hardware, but also to see how this hardware fits with the algorithmic design. The ultimate gains are going to be achieved only if we combine two together. And then, okay, let's think about the hardware, and more specifically, what is that is producing this inefficiency? I already said and sort of showed that the models that we have today are really large. So we have a lot of data to deal with. We also need to store all the model parameters, and our current computer architecture is not well suited for this. We have what is called von Neumann architecture, which sees a very clear differentiation between the compute units and memory units. And actually, most of the time and most energy that we waste, it's not on the compute part of the operation, but actually for transfer of data. That is very nicely illustrated on this table. You can see that any particular mathematical operation doesn't take that much energy. But once we get to needing to fetch the data from either on-chip memory and especially off-chip memory, that the energy consumption goes up dramatically, maybe many orders of magnitude. So we have what is called von Neumann bottleneck. That's really what is limiting the performance of our current hardware that we use for AI. So then we had in the last few years, there's many different approaches on the circuit level, how the people are trying to improve on this. And of course, today we have the GPUs, which are the main approach, especially since 2012, where GPUs are now deliberately designed to do AI applications. We also have the things such as ASICs, application-specific integrated circuits. The example, or maybe the most famous example, being Google's tensor processing units. And the aim of these designs is basically try to improve the performance both of the memory or the memory bandwidth, how much data we can transfer from memory to compute units, and also to do more operations in parallel. So this is sort of higher level philosophy of the whole approach. We started with the CPU architecture. We had maybe a few cores and some shared memory, or some global memory. But then we went to a GPU architecture where we have many more cores and this memory to be much more shared. So what we are trying to do is to increase the bandwidth and also try to break this von Neumann bottleneck, at least to some extent. We can think of if we can expand the whole approach to now go not only on the level of the circuits and some functional blocks, but actually to go to the level of the individual devices and maybe even nano devices. So to really push this, that even the nanoscale devices could do both some level of compute and storing. So really try to break von Neumann bottleneck on the lowest level. I already mentioned there is a lot of algorithmic solutions we can think of. So one very significant one that has happened is the way how we represent data. And this is really important. In the past, for kind of generic computing, we are typically using high precision computing. And what that means is that we are using a lot of bits to represent the part of data. For example, to represent the weight in the neural network, you can use quite a high precision, so maybe floating point 64 or 32. But we figured out that actually, by reducing this precision, going from FP32 even to integer 16 or integer 8, especially for inference, we can live with that. And then this has some profound effects on energy efficiency. If we can, let's say, work with the lower precision, we don't need to use as much energy. So you can see that, for example, comparing 8-bit multiplication to 32-bit multiplication, can see how that scales in terms of the energy, and also real estate on the chip, which is quite important. So this is example how NVIDIA was able to use these algorithmic and hardware co-design to dramatically improve the performance over the last few years. Since 2013, the performance of the GPU cards have went up by the factor of over 300, which is not something that is expected only by Moore's law. So there's definitely a lot of very good work and good improvements that we have seen over the last few years. But even with this, if you start from the digital approach and then this use the architectural solutions and reduced precision computing, still we might not be able to improve much beyond maybe what is today, and maybe by factor of 10 more or maybe 100 more. So it seems that we need to consider something new, maybe to think about even more fundamental approaches and innovations at the lower levels. So there is something new maybe that we can come up with that would then help our circuit designers to make and design even smarter and more energy efficient chips. So this is the part where I'm going to introduce the concept of a memristor. So what is the memristor? Well, memristor is a whole new electronic component. It was introduced by Professor Leon Chua back in 1971. He was looking at the basic circuit elements and these basic observables, voltage, current, magnetic flux, and charge. And he recognized there is a broken symmetry. So there is something that should be connecting magnetic flux with charge, but it seems that component was missing. And then the hypothesis was that such component needs to exist, and he called it memristor. The reason why it's called memristor, if you play with the sort of basic equations, you can get quite a generic expression, looks like a generic Ohm's law. But the difference is this value, which is typically resistance, which connects voltage and current now, is memristance. And this value is not a static value. It's not a constant value. It can change depending on the history, what happens to this device. Then on the more practical level, we have seen that in 2008, HP Group came with the titanium dioxide nanoscale implementation of a memristor. It was a very simple sort of structure. It looks like a capacitor, but the special thing about this device was if we are to apply the voltage across the terminals of this capacitor, it is possible to change the resistance of this device in a very controllable way. So if you look at the IV curve, current voltage curves, this is the signature of the memristor device. It's not just like a straight line as we would expect with a resistor. Actually changes it changes dynamically depending what happens to this device. Very similar technology was considered or developed even before then. It wasn't linked to the memristor, but this technology was called, or still it's called, resistive RAM technology, resistive random access memory, which is basically the same concept. We have these capacitor-like structures. We have two electrodes, and in between is this switching layer. These days, the most popular choices are transition metal oxides. So what is possible to do is to change the resistance of this device by changing the resistance or conductance of the metal oxide layers. And this was considered for the memory application. So if you can change the state of this metal oxide device to go from the conductive to the resistive state, you have the potentially the representations of zeros and ones that you can use for the memory. And this is the non-volatile memory. So that means once you set the device in the particular state, you can then just leave it at that state without changing anything, and it would remember the state. Now, if you treat it only as a memory, it is only natural that you compare it with the kind of the memory we use today. That's a flash memory. And you can see that resistive RAM on the fundamental level beats flash almost all categories. So you can see that endurance is better. Potentially, we can scale these devices beyond what is possible with flash. It is much more energy efficient memory. It is much faster memory and so on. There's a lot of challenges. So this technology is still in development, and there's some small scale chips that are being produced today and sold, but still there is a lot of work to be done. So what is the physics behind this? So this is just for people who might be more interested in materials design. This is a small animation that tells you what might be happening in here with ignoring a lot of details. So if you look at this, schematic here, what we basically have is 2 electrodes and the metal oxide or some other oxide in between. And this is nominally an insulator. But then once we apply the voltage, what is possible is to remove some of the oxygen ions from this oxide matrix. And what is left is the sites called oxygen vacancies. These oxygen vacancies could conduct the current. And what you see is that once you produce the conductive filaments, the conductance of your device changes. So it goes from the very resistive state to the quite conductive state. And you can reverse this process as well. You can, for example, reverse the polarity, get some of these oxygen ions back into the oxygen vacancies. You can recombine them and then recover the resistive state. So you can do this back and forth many, many times. And that's quite appealing for the memory applications. We at UCL are working with one particular material system, and that is silicon oxide. So we are using silicon oxide to do the switching. And the reason being is that, well, silicon oxide is the most used, the most understood, probably the cheapest material in the CMOS industry. So we would like to stick with it. And so we are developing this technology over many years, and I invite you to read some of our papers. But apart from just treating this, as I said, as a digital memory to go from one state to the other state, it's possible to operate devices in much more gradual way. So to treat them as the analog resistors, where the resistance would change much more gradually, so you can then achieve many different resistive states, not only 2. And why is this interesting? Well, before I tell you that, this is just a snapshot of the materials research that we do. So I said that we have spent a lot of time and effort optimizing these devices, but what is specifically that we do? Well, it is really important that you understand the physics of switching, and there is a lot of details that are quite relevant and interesting. So for example, you would need to think about the microstructure of the nanostructure of these switching layers. What happens once you apply the voltage across the terminals? There is quite a high electric field. The oxygen ions become mobile. Then what is the material that you end up with? Also to think about a bit more fundamental physics. What are the early stages of the filament formations or the formation of these oxygen ions and so on? So I don't have the time to go through all of these, but of course, if you're interested, you can read our paper and please send me an email maybe to discuss if you have any questions. So now going back to this approach where we are using memristors as the analog devices. And this is the way how the memristors could be quite relevant for, let's say, artificial neural networks. It is possible to do max operations in the analog regime in a very efficient way. So how do we do this? Well, we put the memristors in these architectures called crossbar arrays. And then if you apply the voltages at one side of these terminals and sense the current on the other side of terminals, what you basically have is a multiply and accumulate operation in the analog regime, just using physics, basically using Kirchhoff's and Ohm's law. And this is a very efficient way to do max. Basically, it happens in the constant time, so it doesn't scale, at least not scale that much with the size of this crossbar array, and also certainly doesn't scale as the conventional computer architecture that would scale quadratically with the size of the matrix. And also, this is in-memory compute, which means that you don't really need to fetch any data, that the data is already there. The same approach could be applied for doing the physical artificial neural networks, so basically to try to implement ANNs physically with the crossbars of memristors. And both approaches would give you much benefits, so many orders of magnitude improvements in energy efficiency. So this is just to give you the examples of type of the improvements we can see. So this is the work, very nice work being done by IBM, and they shown that in principle you can get the orders of magnitude better energy efficiency compared to the current state-of-the-art GPUs and ASICs. And this is basically this gap. Maybe, and there is still a sort of open question, maybe we can use the analog devices and analog processing to do AI beyond what we are doing today with the GPUs and reduced precision digital compute. There's a lot of issues, as I said. Once you go to the analog processing, you need to deal with the device non-ideality. There's a lot of device variability. There are some faulty devices and so on. You can think of how to improve that on the materials level. So as I said, there is a lot of interest in physics, a lot of materials engineering, how to improve the performance of switching. So for example, this is how you go from the devices with a high variability to the much better performance just by engineering the interfaces between the oxides and the metals in your memristic devices. You can also think about some system solutions. So for example, this is just the work that we have done with our friends from University of Massachusetts. We considered using chips of 8K memories and seeing what is the variability and let's say yield with these devices, and then try to construct some system solutions to work with NNs. So this particular solution, it's called committee machines. So you can think of to maybe not construct one large neural network to do this certain application, but maybe having the committees of the smaller neural networks. And it turns out to be that even when you're using the same number of memristic devices, if you have a committee of the smaller neural network, it works much better than if you have one large one. So you can see the examples, for example, how you can recover. This is the software level solution. Then there is the drop because of the non-idealities. But then when you consider using the committees of neural networks, you can see how this accuracy could be improved. And eventually you end up with the software level accuracy. So again, many more details in this paper. And this is quite a holistic, well, quite generic approach. You can applied to deal with almost all types of non-idealities that you face with this technology. And finally, only the last few slides, we can think about the approaches even beyond this. Maybe analog processing is going to give us the gains for a couple more orders of magnitude, but then there is still a lot of space to get to the energy efficiencies of the human brain. And there is a lot of open questions, of course. But there is a whole approach and the whole industry now that is considering designing neuromorphic chips. And these are the chips that would operate much more like human brain or the biological systems. So it is, of course, true that we don't know everything about the human brain, but we can use some of these concepts to be inspired and maybe to apply to other artificial systems. So one thing that we know of is that the processing in the brain, we think, is happening with the spiking, not with the continuous systems. And there is the whole area of spike neural networks, which is not the most conventional approach, but still it's quite interesting. And it is important to consider, can we construct the hardware substrate, so the hardware devices that would be able to implement the most useful and the most important functionalities, that being the synaptic plasticity and also neuronal spiking. So we see how, for example, the memristic devices could implement the synaptic plasticity of the real synapses, and also how these devices could be used to generate the spiking. So these are the two fundamental functionalities that we would like to have for implementations of things such as spiking neural networks. Of course, many open questions. We don't know what are computational primitives in human brain. There is a question, do we get the gains of energy efficiency with what kind of the signals? What is the basic nature of training in spiking-based neural networks? Maybe there are a few other themes such as asynchronous computing. When is that beneficial? Maybe we can use a time to do the computing, which is really interesting. And also to think about the systems beyond the narrow AI. If you're interested in more about how all of this fits within, how memristors fits with these different concepts, there is a review paper that we published last year, and you can see how memristors could be applied for something which is sort of basic digital memory to in-memory computing to then deep learning acceleration, maybe with the analog approach, but also for the concepts such as spiking neural networks, even beyond something like reservoir computing. This is not something that only happens in academia. There is a lot of industry that is interested in this. So, for example, you can see how IBM works very heavily on this subject with their phase change memories. Very impressive, very good work, and many other companies also. And with that, I would just like to thank our sponsors. So these are the sponsors and also the group. If you're interested in the subject, please just mail us. Maybe we are always looking for a good PhD student. So if you're interested in this area, we are always open to have a chat and to see would you like to join us. Okay, with that, I would like to finish my presentation and invite if there are any questions.
Thank you so much, Dr. Adnan, for the stimulating contribution. It was a wonderful talk. There are a couple of questions. The first question is from Vishaka. You mentioned the algorithm we use to train AI are old. Do you think the recently trending program language Rust can improve power efficiency to train AI?
Yes, that's a very, very interesting question. So when I say that the algorithms are old, that basically means that the basic principle, how do we apply it's old. So things like basic backpropagation algorithm is quite old, but it is true that we are continuously developing these algorithms. So we are improving on the performance of the efficiency and so on, but maybe we need something completely new. Maybe beyond backpropagation algorithm, or maybe it's here to stay, but for the certain class of applications, maybe we can think of the different algorithms. So certainly it is improving, but in the end, it's also the question about the hardware. Do we have a hardware that is energy efficient? That's basically where we are wasting our energy.
Okay. So the other question is from Jobin Varghese. How does the artificial intelligence and machine learning framework exploit the future memristors research?
Yes, so memristors is this very fundamental technology. So it's basically on the level of transistors. You have this fundamental piece, the device, that you are then trying to apply and fit within the framework of the circuit design, then algorithms and higher. So it's basically starting for the most fundamental level. It's basically from atoms up all the way to applications. And then you can think of, okay, what is that is the most relevant part that happens on, for example, GPUs? Where is the memory wasted, or where is the energy wasted, where there is a hope to improve on the energy efficiency, and you start to build from that. So as I said, you can treat the memristors as a digital memory, as the analog memory, as the spiking sort of proxies for the spiking computing, and so on. So many different levels and many different approaches you can use it.
Thank you for the clarity. So the other question from Bibi Mary Francis. Why is overfitting of data not considered good in machine learning?
Right. So again, I'm not the expert in machine learning, but from my understanding is that if you have overfitting, you basically end up with the system that would just memorize the answers. So basically, if you train it on the particular set of data, it would be extremely good, almost with 100% accuracy of giving you the right answers on the training set. But then if you show it some let's say the example of some data that hasn't seen before, it can't generalize that, and it would give you completely wrong answer. So it's basically the balance about to try to come up with some rules or with the pattern in data and just memorizing the data. So overfitting is not good for that.
So the last question is from Makesh Waka. How machine learning is associated with energy storage, and can we predict the efficiency of the system using machine learning?
Yeah, that's an interesting approach. It's the other way around. So this approach is mostly like, let's improve the machine learning. But if you then think, okay, let's apply the machine learning to improve something that could improve the machine learning. So maybe there is interesting feedback that happens there. But the storage, the energy storage, and I mean, if you just, if this is the question about the memory, it's the fact that other models are increasing in size. So what that basically means, you need to have enough memory to store all the components of your model. And that memory needs to physically be stored somewhere. So what is the part which is inefficient or which is limiting is when you get your data, let's say the parameters of your model from the memory to the compute units, you're losing a lot of time, a lot of energy. So you would see if you just check, let's say any typical GPU system, there is two metrics that you wanna look at, and that's the memory bandwidth. So that means how quickly you can get your memory from the memory to compute, and also what is the computing performance. So things like how many gigaflops or teraflops you can do. So those are the matrices that are important, but memory is really limiting factor because you need to think how quickly you can get that data.
There's one more question from Girish. So if you do patterning of memory devices, the active layer of patterning the active layer by using lithography, what are the benefits?
So let me just, can you repeat the question? I didn't quite hear the first part, sorry.
Yeah, I mean, so the question is, if you do patterning of memory devices by using lithography, what are the benefits?
Right. Okay, so I mean, lithography is quite generic approach. Lithography just means how would you pattern any sort of electronic device. It doesn't need to be applied only to memristors. What is point here is that you are trying to break down this abstraction where you have, let's say, the functional units that would do the memory and the compute. And then basically this abstraction also is very successful, quite generic, and you apply for many different things. It's not that energy efficient. So what you're trying to do is to say, okay, let's now go a bit more to the physical level. Let's try to implement some functionalities by physics rather than by digital design. And by doing that, you can really at least hope to have much better energy efficiency. If you try to implement functionality directly in physics of the devices, it is typically much more energy efficient than if you need to build, let's say, hundreds or thousands of these devices and then try to do the conversions from one to the other.
So much. Yeah. So if there are no questions, we'll close the session. Thank you once again, Dr. Adnan, for this wonderful lecture. Thank you very much. Yeah. See you in another.
Thank you. Thank you so much. This was a great opportunity. Thank you all, and thank you for your attention.
Thank you.
Bye-bye.
So,